All right, welcome back to Easy Math with Nick. It's been a hot minute. Went on vacation for a week, and then the week before that, I took a short break. Didn't realize it would snowball that quickly. And look at me now, another 2 weeks later, making another video. So today we're on video number 15. As I promised in our last video, which got a decent amount of views, we are doing an AP Physics and Mechanics question today. I thought mechanics. Did I spell mechanics right? Okay, good. Hopefully, imagine I didn't spell it right. That'd be funny. But what I was about to say was that today's video was originally going to be the 2024 exam, or I was thinking either 2024 or 2025. But I decided to go with this question, free response question number 3 from the 2021 AP Physics C exam. So, just a short note here before we begin. How this exam is set up is completely different 4 years ago to compared to how it is today. So just take that as take how I solved this question with a grain of salt in terms of like time, because I don't know where I'm going with this. Let's just begin. Okay. Let me read the question first and we'll begin. Haven't tackled this before, so it's brand new to me, but it looked interesting, so we'll work through it together today. Number 3, a triangular rod of length L and mass M has a non-uniform, that's important, linear mass density given by the equation lambda equals another Greek letter, x squared, where that other Greek letter equals 3m over L cubed, and x is the distance from point P at the left end of the rod. Using integral calculus, scary, show that the rotational inertia of the rod about an axis perpendicular to the page. Don't worry about that part. It might be hard to imagine, like perpendicular to the page, whatever. And through the point P is 3/5 ml squared. Okay, so they give you the answer. They ask you to prove it, right? So, okay, they gave you this constant here. So let's substitute this into the equation. We have lambda equals 3m over L cubed x squared. So I just substituted in what they gave us for that other Greek letter that I cannot remember for the life of me. Whatever, I should know that, but it's okay. That is just me substituting in what they give us. But now we need to use integral calculus to find rotational inertia. That's what they're asking us. So we know that rotational inertia equals the integral where dm is some change as a mass differential, right? But we need to solve an expression for dm in order to substitute that in, because we're not able to evaluate this integral right away, as we're dealing with units of measure of length there and units of mass there. So we need to start off somewhere. And to get this out of the way, I'm not going to put in our limits yet because it won't make sense until we solve for dm. So I'm not sure if this is provided on the equation sheet, but it's important to know that lambda is, as it states, that's our non-uniform linear mass density. So lambda describes the change in mass with respect to length. So I should put dx because that's what they give us for length. That would be confusing otherwise. So lambda is our change in mass with respect to length. They tell you that. That's what non-uniform linear mass density. That's what lambda is describing, the change in mass with respect to length. That's what that means. So now, if we multiply both sides by dx, we can solve for the mass differential dm, and plug that into our integral that we got from our equation sheet that I don't have right in front of me, but hopefully you have it in front of you when you do this on your exam. So now we bring down the lambda we had up there, and put it in there. So we'll have dm equals 3m L cubed x squared dx. And so now we have an expression for dm. We can plug in right there. So now we'll have equals, I'll put in our limits in a second. The equation on the, the expression on the equation sheet uses r for length, but now because we're dealing with x, I'll have x squared instead, as I think that'll make more sense. So we're going to have x squared here. I'm not changing anything. I'm just using the correct variables as the problem requires. So I'll use parentheses here to make the substitution even more apparent. this is what we're doing now. And we're finding the rotational inertia about an axis perpendicular to the page through point P. So our limits are going to be from x equals 0. So we'll just say 0 to L, because we're going along the full length of that rod there, the non-uniform rod. So now if we multiply what we have inside the integral, we're going to have integral from 0 to L, m over L cubed x to the 4th dx. And what we have here is a constant, as we mentioned before, so we could pull that out of the integral. So I'm going to do that in an adjacent step right here. So we'll have 3m over L cubed, and then on the inside. Now we can evaluate that integral. So we're going to have, we'll say I again, rotational inertia. So we're going to have 3m L cubed times, I use another symbol for multiplication, not x, that'd be confusing, right? Once we evaluate that integral, use brackets, integral of x 4th dx and 1/5, basic calculus right there, right? And we're valuing from 0 to L, so it's going to be 3m L cubed times 1/5 L to the 5th minus 1/5 0 to the 5th, which is just 0. So I'm not going to write that. But, so we'll have L to the 5th over 5. And now some things cancel out here, right? Our L's cancel. So we're going to have a 2 there. And that's all that cancels, right? So we'll finish with 3/5 mL squared as our rotational inertia. And thank goodness that is what they tell you the answer is. So this question is more of show your work. You might have been told by your middle school teacher in math class, always show your work, right? I know that 3 times, whatever, I'm not going to give a basic example. But showing your work here is the entire question they're asking. Getting the answer gets you no points here because they give you the answer. So your work, showing every step is very important. Except for when you're evaluating the integral here. I didn't show any steps there because I'm evaluating from L 0 to L. And that's pretty explanatory there. Yep, showed all my steps there. Let's move on to part B. Okay, determine the horizontal location of the center of mass of the rod relative to point P. Express your answer in terms of L. Oh, that's important. Okay, express your answer in terms of L. So not like R or X or whatever. Don't know why you would do that anyway, but horizontal location. Okay, yeah, obviously, right? When I find the vertical location, we don't have anything to work with there. Okay, so now, as we covered in a prior video, we should know that to find the center of mass of the rod of a non-uniform object like this, we're going to take advantage of the expression. I'll take this down here. We're doing part B now. Might have to make more room. This was like one of our first videos, right? 1 over total mass, integral from, just say A to B, two locations, two lengths, 2 different lengths, x dm. So that mass differential comes up again. And so we want to find a center of mass of the rod relative to point P, express your answer in terms of L. So we know the total mass is big M, so we can leave that unchanged. And I think our limits are still going to be from 0 to L, because now we're still dealing with what? The whole rod relative to the center of mass relative to point P. That's the limits are from 0 to L. I think that's self-explanatory. I guess you can do it a different way if you'd like, but I don't see changing our limits to be very advantageous here. If you have any other input on that, let me know. And then we still know, we still have the mass differential from up here, right? So we can take use of this again. We don't have to do the work again because we did all that work up there. Nothing changes. Everything from part A is still true for part B, except for the fact that our integral is going to work different because we don't have x squared. We just have x. So now we have 3m over L cubed x squared dx. We have x 3m over L cubed x squared dx. I think that was what we had, right? Let me look again. Short-term memory. There you go. Okay. And now we could pull out That constant again. Yada, yada, yada. This should be repetitive, right? We're going to have 3 over L cubed. 0 to L, x cubed dx. And now we can evaluate that integral because that's just a simple integral similar to what we saw before. So XCOM. I think that's a good video game. I should try XCOM. Heard of it before. 3L squared, that's the constant we pulled out, like we just did in the last question. Sort of similar, going through the same motions here. But now we're going to have 1/4 x to the 4th. Once we find the antiderivative there, fun calculus stuff. I'm not going to evaluate the lower limit. That's just going to be too much of an effort on my part. 3/4. Okay, so we're going to get... Let me show the work here. I don't want to go too quickly. We have time. 3L squared times 1/4 L to the 4th. So what this is going to look like is we're going to get some canceling with the L's there. So we're going to have 3/4 L squared, L to the power 4. Let me make sure. Does that make sense? I have a feeling that doesn't make sense. We should be in units of just meters, not meters squared. It doesn't quite make sense. Just give me a moment here. I looked it over, and I think our work still makes sense. Even though our units might seem a little bit off. When we square the length and then divide by 4. Yes, well, we will be in meters squared, but that's still... I think you still get a center of mass value. You still get the at least the magnitude, just that straight value for the center of mass. So I'll come back to that. But I think I did everything right there. We had the mass differential correct. The total mass is m. Just making sure. Yeah, length L, mass m. That much doesn't change. Oh, I think I messed up. I think I had Yep. That's my mistake here. This should be L cubed. Okay, I just found that out now. Good. That should be L cubed. Okay, I told you, short-term memory, right? That's just something that you won't make a mistake on the test because you're not doing your test on a giant tablet like me. I knew something was a little bit off. Okay, so this should be L cubed. So this is going to cancel out. Oops. Cancel out to be 1. So that's just going to be 1/4 L. Okay, there you go. That's our answer. That makes much more sense now. I'm going to circle that in blue. That's our answer for part B. Okay, great. Now let's go on to part C. All right, that was a good catch I made there. For an axis perpendicular to the page, don't think too much about that. If you understand that, great. If it's hard for you to visualize, don't sweat it. Just as before. Is the value of the rotational inertia of the rod around point P greater than, less than, or equal to the value of the rotational inertia of the rod around center of mass? Okay. I hope that when you read this question, your first urge is not to find the rotational inertia around the center of mass. Or necessarily to find... yeah, you don't... You in part A, you solve for it around point P, right? Perpendicular to the page to point P. Yeah. And now they ask to compare that to around the center of mass. They don't ask you to actually find the value of the rotational inertia around the center of mass. But if you wanted to, you could. But the easiest way to solve this question is by utilizing what's known as the parallel axis theorem. Because parallel axis theorem, it's very not common in this AP Physics C curriculum. You very rarely see questions on it, especially in the new curriculum. I think they even removed it. But essentially, it states that the rotational inertia of what's known as I subparallel, or the what's up the parallel axis. I'll make that make sense in a second. This is what's known as the parallel axis theorem. And what this essentially states is that the rotational inertia of an object through its center plus the distance to a parallel axis, plus md squared, where d is the distance from COM to parallel. I could have just did the parallel symbol. axis. And so this is how you relate the rotational inertia of an object through its center to that of a parallel axis, the distance d from that center. And so this is really useful if you're given the rotational inertia of an object through its center and you want to find the rotational inertia of that same object through an axis that's parallel to that going through its center of mass. So this is hard to visualize, right? I said that for an axis perpendicular to the page, this sort of incorporates that idea where, well, it's perpendicular to the page just means that sort of popping out of the page, right? We talked about something like that in our last video in a completely different context. But here, the other axis, the parallel axis, is still popping right through the page, right? And so that in that way, it's not going to intersect the axis going through the center of mass. So it's parallel. That's kind of what we're getting at here. And so essentially, without even knowing any of the values of the rotational inertia, center of mass, or through point P, just a little heads up here, the rotational inertia of the rod around point P, that is what we kind of call our parallel rotational inertia here if we were to utilize this equation. Because the center of mass is what, the I center is what's the rotational inertia around the center of mass, right? So this is, we don't know. We don't know this. We know that. So if we really wanted to, we could, and we can find this. We could find that if we wanted to, right? Because we know the distance between the center of mass and point P. Because point P is at what? X equals 0. And we found where the center of mass is, right? Relative to point P. That's what we did in part B. So if we really wanted to, we could find the inertia through the center, the rotational inertia of the rod around its center. Center of mass. But we don't need to do that because all it's asking is to compare the values. So if we know that I center plus md squared is equal to I parallel, that must mean that I center is less than I parallel. So that is just a fact we gleaned from the parallel axis theorem. So I know, and in the context of the question, this means that I center of mass is going to be less than I through the point P. And so around point P, then point P is greater than, the rotational inertia around point P is greater than that of the rotational inertia through the center of mass, if we just flip the inequality here. And I'm not going to write the whole explanation, but you could just say, according to the parallel axis theorem, the inertia through point P must be greater than the inertia around the center of mass, because you would have to add that md squared term to get to the rotational inertia through the center of mass to get the same value as that through the parallel axis, which is through point P. So that necessarily means that the rotational inertia through the center of mass must be a smaller value. So, because this term cannot be negative because its mass is positive and distance is squared anyway, so that's going to be positive. If you really want to get into the nitty-gritty of why that is. But hopefully that made sense. If you really wanted to, you could solve either by using parallel axis theorem, or if you don't know it, you can use integration to find the rotational inertia through the center of mass. I'm saying rotational inertia so many times, it's sort of tiring me out. But if you really wanted to, you can find that and then directly compare the two values, and that sets you up for a very easy explanation. But there's a lot of work leading up to that point. And if you get any of the work wrong, they could take off points. So I think this is the most easiest way, the most effective way to tackle that question. So it is greater than. Let's move on. On Explo, sketch graphs the magnitude and net torque on the rod. Okay. I think I did not include a part of the question here. So what's going on here, if I remember correctly? Oops. Let me take a picture. I'll be right back. I got rid of a picture of part of the question. That's very important. I'll be right back. Okay, so I paused the video. I almost forgot how to do that, but this is what we're doing here. The rod is released from rest in the position shown, and the rod begins to rotate around the horizontal axis perpendicular to the page and through point B. Like I said, don't worry about that, but just know that its axis of rotation is going to the point that's rotating around is point P. I think that's what they're getting at there. That's all you can take away from that. So if we look at the question, we're starting horizontal position, and then sort of like a door hinge. That's not a great comparison, but we're think of this two-dimensionally. It's sort of that horizontal position. Now it's going to be rotating down into a vertical position. That's what's going on here. And now we're going to be sketching graphs of the magnitude of the net torque. Magnitude, that's important. There's no negative quadrant here anyway. And that graphs of the angular speed as a function of time until we get to that point where the rod is vertical. Essentially, when the center of mass reaches its lowest point. That's another way to say the same thing. When the rod is going to be vertical. So let's get back to our question. This is where the restoring torque really comes in. If you remember from our video where we derived the period of a physical pendulum, you'll know that in a scenario just like this, net torque is going to be equal to... oh, wait, did we do this in that video? Yes, I think we did. Okay. Yep. Yes, I think we did do this. Okay. It's going to be some constant. You can solve this constant, but times theta. So the constant is going to be something like negative mgr sine theta, mgr, or something like that. Yes. Yeah, it's going to be something like mgr is going to be our constant there. And because we're dealing with small, I don't want to explain the entire reasoning we had in that video, but because we're dealing with small angle, sine of theta is going to be roughly equivalent to theta because of the small angle approximation. But that's all in that last video. So it's going to be something like mgr. That's all to take away from that. That's what that constant is going to be equal to. But that's not important here. For the reasoning of this question, what you need to know is that as theta increases, as the angle, which is the angle to the vertical, as we start swinging down, let's say this rod is at swinging down from, this is our point P, and it's swinging down, our angle to the vertical here, that's the angle we're dealing with here. As that angle increases, if we look at our equation here, our torque will increase. So what the magnitude of the torque will increase. But what's going to happen here is that as the rod swings down, the angle is actually decreasing. So if our angle decreases, the magnitude of the torque is going to decrease. And thus, as our inertia is constant, so will angular acceleration. But that's not what they're asking here. They're just asking torque. Never mind. Forget it. Scratch that. I didn't mention that. So what's going to happen here is that torque is going to be decreasing. So it's going to look something like this. It's going to teeter out until we get to that time. Until we get to the time at its lowest point. So this is our T low. I'll call it T low. That is the time at the lowest point. But our angular speed, that's a different story. That's not going to be decreasing. It's going to be increasing the entire time, because our torque doesn't. Our torque and angular speed are going to be in the same direction throughout this entire throughout the entire time as we go from horizontal to vertical, as the rod goes from horizontal to vertical. And so what's essentially going to be happening here is, although the torque is decreasing in magnitude the entire time, that still means that there's a positive angular acceleration, and that still means that throughout the in the context that the angular speed is going to be positive the entire time, that means that the angular speed will be increasing the entire time. So it's going to be like an upward curve until we get to that point T low, at which we're going to hit a maximum angular velocity. And at that point, that should, when we look at our graph, it's going to have our tangent, the line tangent to the curve, which is the angular acceleration at that point, is going to be 0, which makes sense, right? Because look, what is our torque, our net torque at that point? 0. So that makes sense. So the features of our graph check out. I don't know if they curved it the same way I did, but it's definitely a curve. It's not linear by any means. So that is what it is. So hopefully my reasoning made sense there. But just to restate, the reason why it flattens out at T low, if we were to go past that point, it would start going in like the other direction. It would form like a semicircle, I'm pretty sure. But that's not our concern here. Our concern is that at that top point, when angular speed is the greatest magnitude, the slope of that graph is going to be 0, which means that our instantaneous angular acceleration at that point is 0. And what that really means is when we look at our torque graph, at that point, our torque is going to be equal to 0, because torque is inertia times angular acceleration, right? Torque equals I alpha. We know that, right? And so if alpha is 0, torque has to be 0. So that's why the features of our graph make sense. Okay. There you go. Now, finally, part E. As the rod rotates from the horizontal position down through vertical, is the magnitude of the angular acceleration on the rod increasing, decreasing, or not changing? Okay, this is why I was thinking of angular acceleration. Maybe I subconsciously read ahead without even knowing it. If we look at our graph here, our graph is horizontal down to vertical. So we're dealing the same scenario here. Our torque is going to be decreasing. The magnitude of the torque is going to be decreasing the entire time. So naturally, because torque equals I alpha, as torque decreases, so angular acceleration will decrease as well, if we're just looking at magnitudes. So the answer here is decreasing. It's not changing, because that would imply a constant torque, which is not true here. Our torque is changing because our angle theta is changing, and torque is dependent upon that angle theta. And therefore, if our torque is changing, our angular acceleration is changing, right? So that can't be true. It's not changing. Increasing, or if our angular acceleration was increasing, that's implying that after we hit that bottom point, we're gonna just start. It doesn't really make sense in context. I don't know how to explain the wrong reasoning, but it is not increasing. I explained why it is decreasing because, as we just explained, the net torque is going to be decreasing because the angle to the vertical is decreasing, and that is what we're looking at when we're looking at our torque equation. If you want to get real fancy and you had an expression for torque that dealt with an angle to the horizontal instead, let's call this I don't know, sigma, whatever. Who cares? If we had sigma instead, we would have like negative mgr cosine theta instead. And this would still be valid because here our angle to the horizontal is increasing. But this still, regardless, we're in the same scenario here for these two examples. Same scenario, we're just looking at different perspectives. Now we're looking at the angle to the horizontal, if that's the way you want to solve the question. But if you look at a cosine graph, let's look at our cosine graph, right? We're dealing with small angles here. Our cosine graph looks something like this, right? Oh, let me think of a good way to, that's not quite right. It's going to look something like this, right? So for our small angles, we're dealing with stuff like roughly below like 180, roughly below 90 even. As our angle increases, cosine of the angle decreases. So if we look at our expression over here, as the angle increases, cosine of theta is going to decrease. So really, that means our net torque is going to decrease as well, because if this goes down, everything else is constant. Mg, R is all constant, right? So torque is going to go down. So in the same scenario, just looking at two different perspectives, the torque will go down either way. Torque will be decreasing, the magnitude of torque will be decreasing either way, which by necessity means that the magnitude of angular acceleration is decreasing. So that is if you wanted to look at a different perspective, right? I'm sorry. I think I meant to put rho. I'm sorry, rho or sigma here. Meant to put a sigma there. And if I'm using a different letter, I should indicate that, right? I'm only using sigma here because that's what we used here to indicate angle to the horizontal, just to show if that's how you want to think about the question. Either way, as that angle increases, as the angle to the horizontal increases, or alternatively, the angle to the vertical decreases, the torque will decrease. The net torque will decrease either way you look at it. So no matter what way you look at the question, you will get the same answer. If you want to say cosine sigma, go ahead. Doesn't matter what you call it, but for sake of justification. And that is why it's decreasing. I think I covered that pretty in depth. The only thing I would want to go back to is nothing. I think that's all I want to cover today. Hopefully I did that all right. I think it's good. My graphs, I'll take a look at the official scoring guideline. Usually I don't do that, but I want to take a look at that to see how close I was with my graphs. I think they look pretty good. If you really want to extend your graph all the way to time t, I would suggest doing that. I did not, but if you could get the point there, because I think this time t is the time it reaches its lowest point. And it's okay. I just called that t low. I made up a variable. Whatever. I think that's all I wanted to cover today. Sort of got a little tired in the toward the middle there of saying rotational inertia like 400 times. But that was a fun question. And that's it for today's video. I think my next video will be another physics free response question. And I think then after that, I'll go back to statistics for another video. But that's it for today. Thanks for sticking by. This was a fun one. Easy Math with Nick, video number 15, signing out. Thank you for watching. See you in the next video. Oh, and just one final change here. I know I said goodbye already, but just when I was doing my final check to make sure I did every part of the question, whatnot, I noticed something really silly here. This last step here, when I was so focused on accidentally having an L squared for part B here that I forgot to multiply it times 3. That was something I almost didn't catch before uploading. But there you go. This is really 3/4 L. And I looked everything else I did correctly. I think my graphs look right too. And that's everything. So now it's 3/4 L and not 1/4 L. I forgot to multiply by the 3 here. Okay, that's about it. Just want to add that at the end there. Thank you for watching. See you next video. Should be another physics related, as I said like a minute ago already. But thank you for watching.